Well, good morning, good afternoon, good evening to everyone. It's a real pleasure today to have Professor Keita Yoshioka to speak to us in this seminar series. And Dr. Yoshioka, he received his Bachelor of Science in Resources and Environmental Engineering from Waseda University. That was in Japan in 2003. And his PhD he received from Texas A&M University, and that was in 2007. Following that, he joined Chevron's geomechanics team in Houston, and I see some representatives there who have come to listen to his talk. He conducted internal consulting and corporate research on various geomechanics problems for more than 10 years, and that included the short-term assignment in Chevron's geothermal operation in Indonesia. But then in 2017, he moved to Germany and he started working on an open source code development project at the Helmholtz Center for Environmental Research. And there he focused on computational fracture mechanics. Since 2002, he has been a professor for geoenergy production engineering at the Department of Petroleum Engineering at Leoben University. And a real pleasure to welcome Professor Yoshioka.
Well, thank you very much, John, for kind introduction. Okay, so I will start my presentation today. So I'll talk about fracture initiation and propagation using the variational phase field model. So I suppose that some of you, or maybe many of you, might have heard about phase field models for fracture. It's becoming very, very popular these days, and I started in computational mechanics community, and then it has been applied to hydraulic fracture these days. So I added this variational. So the phase field model was originally developed for numerical method to treat sharp interfaces like phase changes, and then it has been applied to fracture mechanics in the last 20 years or so. And I added this word variational. So the phase field is a numerical technique to regularize sharp interface, but the other aspect of this methodology is about this variational approach. So we are talking about energy minimization. So I'd like to start with this slide. So as I was introduced, I was in oil and gas industry for many years. So hydraulic fracturing is a technique to extract hydrocarbon, or we also apply to geothermal reservoir. But the last 5 years, so I worked in Germany, well now in Austria, but I worked in Germany for Helmholtz Center, and then I was not involved in hydrocarbon research anymore, but I was doing something else like energy storage or nuclear waste storage and so on. And I found that hydraulic fracturing is relevant in this subject, not only the hydrocarbon extraction or geothermal energy development, but even in this storage, energy storage or waste storage, hydraulic fracturing is relevant. But the purpose is different. While in oil and gas, we want to create hydraulic fracture, but in this storage application, fracturing is something that we want to avoid. So the purpose is a little different. And also, because of that, we have to adapt our simulation capability a little bit. So in hydraulic fracturing, in hydrocarbon reservoir, for example, we almost always know where fracture will initiate, because that's where we put packers, or we put we perforate. So that's where the fracture will initiate. But for energy storage project, for example, if we want to avoid fracturing, first of all, we don't know where fracture we're going to initiate. And if you want to assess the integrity or the safety of such project, our simulation tool should be able to predict the fracture initiation. So not only the fracture propagation, but the fracture initiation is one of the focus of my talk today. So then we go to objectives. So the first objective is I want to develop a simulation tool that can simulate complex fracture behavior. And then complex fracture behavior is such as the fracture turning or branching or merging, something like this. So this is an experiment, a hydraulic fracturing experiment we have done, and then we visualize how the fracture behave and interact with the grains. So such a complex fracture behavior is something that we want to simulate. And then second focus, as I mentioned, it's about fracture initiation. So this is a Monterey, so underground research laboratory in Monterey. And there, so this is the large scale experiment for nuclear waste disposal. So there we excavated the tunnel, and then we are conducting this cyclic deformation experiment. So we exposed the tunnel walls to cyclic humidity change. And due to that humidity change, some desiccation cracks will be developed. So this is a very primitive way to observe it, but we painted the scan line with a white paint, and then after time we can see that the new cracks are formed due to the humidity change. This kind of fracture initiation is also my objective. Okay. So then let's talk a little bit about continuum fracture mechanics. So we start with Griffith fracture criteria. So this criteria was proposed in 1921. So if we have a single crack propagation along a known path L, and then we can define the total mechanical energy T, and the Griffiths define the energy release rate. So this is the release energy when this line crack propagated by small amount. So we can take a derivative of this total mechanical energy with respect to the crack length. So that's the energy release rate. And then the material has some resistance to fracture, and that is known as a fracture toughness, or I use this notation G of C. So this is the material's resistance to unstable fracture propagation. And Griffith criteria essentially states that the energy release rate has to be always less or equal to the critical energy release rate, or the fracture toughness G of C. So this is the Griffith fracture criteria, and this is the basis of our continuum fracture mechanics. So if we look at the example, so let's look at this penny-shaped fracture growth. So we have a wellbore, wellhead, and then we have a vertical well, and then we have this penny-shaped fracture, or disc-shaped fracture. And then we pressurize this disc-shaped fracture, penny-shaped fracture, and then we can apply Griffith criteria to calculate the fracture pressure. So the radius of this penny-shaped fracture is R0. Then well, it's more common to use a stress-based criteria rather than Griffith criteria. So it's also known as Irwin's formula. So this same Griffith criteria, if we convert it to the stress, then this is the equivalence. Okay, so this T is the pressure within the fracture, and then energy release rate. It's essentially, we can calculate energy release rate with the loading and the geometry of the fracture. So this R0 is the initial radius of the fracture. And then when this is equal to square root of EGC, or KIC. This is fracture toughness, and then that's when fracture propagates. So then we can solve for the fracture pressure. So this is the critical pressure. So as we increase the pressure of this fracture, and then when this pressure reaches this value, that's when the fracture propagates. Or we can call it frac pressure. Okay, of course we have to account for the minimum stress additionally, but essentially this is the frac pressure. Okay, so this is the closed form expression. But if we look at this expression, what happens if we send initial size of the crack to 0? So you see that this quantity or the frac pressure becomes infinity. And so this is one of the drawback of Griffith criteria. So the fracture initiation cannot be predicted if we use Griffith criteria. Okay, so we always have to assume some small size fracture, and then this is also true when we do simulation. So we have to assume some initial small fracture. So we put some seed of the fracture in order to initiate the fracture. Okay, and another not the issue, but another difficulty of the Griffith criteria is when we have complex fracture paths. So in the previous slide, I assumed that this penny-shaped crack will propagate evenly. But what if the propagation is not even? So, if you have some uneven propagation of the fracture propagation, then we don't have the closed form expression for this energy release rate anymore. And then we have to compute this energy release rate with some other means, such as J integral and so on. So so this makes the complex fracture propagation difficult. Well, a simulation of complex fracture propagation difficult because if we allow fracture to propagate freely in a complex path, then we have to evaluate this energy release rate accordingly. And then this evaluation is not so straightforward if we consider many possibilities. Okay. So this was the Griffith criteria. And 1998, around 20 some years ago, the Frankfurt and Marigo proposed so-called variational approach. So the Griffith criteria, it's actually nothing but the minimum of this quantity. So Griffith criteria states that the fracture propagates when energy release rate is equal to G of C, but this is nothing but the minimum of this mechanical energy plus this GC times L. So if we take a derivative of this quantity with respect to L, then this is what we get. The Griffith criteria is what we get. So it's essentially saying that if we define the total energy as a sum of the mechanical energy, and then the second term is the surface energy. So this G of C is the surface energy density. So if the surface energy density times the area or the length, that gives us the surface energy. So if we define the total energy as a sum of the mechanical energy and surface energy, then what essentially we are doing with the Griffith criteria is minimizing this total energy. Okay, so then we can generalize this Griffith criteria. So we can recast the Griffith criteria as an energy minimization problem. And so if we define some total energy, and then we want to minimize this energy with respect to displacement and the crack set, and how the total energy should be defined. So the total energy we can define as a sum of the mechanical energy and surface energy. And in Griffith criteria, we are only looking at the single crack propagation, but we don't have to limit ourselves to just the single crack, we can look at all the cracks that are available in the domain. So this is just a collection of all the crack, and then this gamma represents a crack set. So then we try to find the displacement U and the crack set gamma that minimizes this total energy E. So that's a generalized Griffith criteria, so to say. Okay. So then we go to phase field. So phase field is essentially regularization of the sharp interface. So we go from the discrete representation of the fracture to diffuse representation of the fracture. So this is the problem we have. So we have some domain omega, and then we have some crack set gamma. And then we want to find displacement and the crack set. We want to find U and gamma that minimizes the total energy in this system. But in terms of numerical implementation, this is not so easy. This gamma or the crack set is the discontinuous surface, the discontinuity. And then if this discontinuity evolves, then it brings all sort of difficulties in terms of numerical simulation, right? Because how do we honor this discontinuous surface with element and so on? So what phase field does is to regularize this sharp interface. So phase field variable, we call it D, and this D replaces this sharp interface. So it's so the sharp fracture becomes sort of a blurred image of the fracture. And then this D, so instead of representing the fracture with the binary system, either 0 or 1, fracture or not fracture, in the phase field, using the phase field variable, we represent fracture with a continuous manner. So in our definition, when B is 0, that's where the material is fractured, and then when B is 1, that's where material is not fractured. But this D changes smoothly from 0 to 1, from fracture to non-fracture. It changes smooth. So there's a transition between 0 and 1. Okay. So so what are we doing? So what equations are we solving? So the generalized Griffith criteria, we can write the problem as follows. So we want to minimize this energy. So the energy is a sum of the mechanical energy. So the mechanical energy is the stress times the strain, and then that's the mechanical energy, and then the second times the surface energy. So this is the discrete problem. So we want to minimize this total energy with respect to displacement and crack set gamma. And with the phase field approach, this energy minimization problem is regularized. So it's replaced with this continuous problem. So the first term, the mechanical energy, so that was a discontinuous integral. So the stress or strain is discontinuous over the crack gamma. We could not integrate over the gamma, but using this phase field variable D, we can take an integral over the entire domain omega. And then the second term, the surface energy. So this was integral over the discontinuous surface, and which is difficult to evaluate. But by introducing the phase field variable D, this also becomes a volumetric integral. And you may wonder why we have this particular form of the equation. And this technique was borrowed from image processing. And what this form of the energy functional guarantees is that so we have introduced new parameter L. This is a length scale parameter. And this length scale parameter controls the transition of the phase field variable changing from 0 to 1. And as L approaches 0, then these two energy minimization problems become equivalent. So that's what this form of the functional guarantees. Okay. And when we extend this phase field approach to hydraulic fracture, we have to add one additional term. So that's the fluid pressure effect. So this term is given by here. And then, okay, so I will not talk about too much detail, but this Bios modulus is also a function of the phase field variable. So by minimizing this total energy, we can solve for the displacement U and then the phase field variable B. And then the remaining variable we wish to find is the fluid pressure. And fluid pressure, we use the Dows's law. So this is the permeability tensor, and then permeability tensor is enhanced using the cubic law. Well, if you watched the last week's webinar, this approach may be obsolete, but I still use it. So this W is the fracture aperture, and then as the fracture aperture changes, this permeability is enhanced, and then also this permeability is given as a full tensor. So I also want to know the crack normal direction. Okay, so that's how we get fluid pressure. Okay, so now I will show you some verification cases. So the phase field representation of the fracture is essentially this. So we have discrete fracture. So we have a line fracture of 2A, and then using the phase field variable, this fracture will look like that. So this red color represent when the phase field value is 0, and then this blue is 1, and then you see that the phase field variable transitions from 0 to 1. And by representing fracture in this diffuse manner, of course, we want to know whether we still can recover explicit properties, such as fracture aperture, fracture length, or fracture critical pressure. And also we all know that the fracture aperture is in the orders of millimeters, while the fracture length is in the order of meter. And this huge anisotropy is actually what makes the computation of fracture difficult, but we have to make sure that we can recover these explicit properties. So we apply our model to KGD fracture. Okay, so the plane strain, and then so we have injection point here. So this is just half of the domain, and we have a line crack. And here is our verification result. So this is the pressure. Sorry, this is the pressure response, and this is the fracture aperture at the injection point with time. X-axis is time, and then this is the fracture length. And we tested our model with different element size. So A naught is the half length of the fracture, and then H is the element size. So so this blue dash case is where we represent initial fracture with 20 elements, and then we refine the element and so on. So then as we refine the element, we can represent analytical solution better. But well, okay, so it's not perfect match, and this is due to the finite reservoir permeability actually. So in KGD solution, the permeability of the reservoir is 0, but we could not really assign zero permeability because of the numerical difficulty. That's the reason for slight discrepancy between the analytical model and our simulation result. But one thing I like to emphasize here is the mesh size. So H is the mesh size. So if we use the small fine elements, so that's 0.1 meter, and then we decrease the element size like that. Okay, but if we look at the fracture aperture, so that's in the orders of millimeters, and you see that even if we use the element size magnitude or 2 orders magnitude bigger than the fracture aperture, we still can recover the aperture change. So if we were to use discrete model, the size of the fracture aperture is sort of the size of the element that we have to use. But with a phase field approach, we can get away with much bigger element size. Okay, so that's the verification example. So then I will show you some of the examples and with focus on fracture initiation. So the first example is an experiment of hydrofracturing experiment in rock salt. So just a cube of the rock salt, and then we drilled a small borehole. Well, my simulation is just a 1/4 of this rock salt, and we put some casing in this borehole, and then the lower part of the borehole is open. So this is where we inject fluid, and we applied 2 different loadings. So the first case, well, obviously the minimum stress is this direction, and then this bright color, you can see that the developed fracture after the experiment. So we expect that the vertical fracture to develop in this experiment. And the second case, the vertical loading was the minimum loading, and we expect that the horizontal fracture to develop for the second case. And in these 2 simulations, we did not put any initial fracture. So we just increased the pressure, and then we let the phase field develop according to the external loading. So this is the result from the first simulation. So on this phase, we apply the minimum loading, and we expect the vertical fracture to develop. So this is the fracture development. And second case, so the vertical loading was the minimum. So we saw this horizontal fracture development, and the initiation of the fracture was picked up. We did not specify, small horizontal fracture or the vertical fracture in the earlier case. So it was initiated just at the bottom of this open hole section, and then this result was based on the quasi-static or the successive energy minimization. Okay, and this example is about the desiccation fracturing. So this was an experiment. This is a plaster, the fully saturated plaster, and then this plaster was placed on top of the frictional plate. So this plate has a very high friction coefficient, and then we let this plaster dry. And so as this fully saturated plaster dries, and then it shrinks, and then first some crack developed on this corner, so this lower left corner on this picture. And these are the images from the top. So from the top, this plaster developed several vertical cracks like that. So in the schematic, it looks like that. Okay. So then we did the simulation for this. So it was a very simple simulation. So we did in 2D, and we only simulated the left half of this plaster, and then we fixed the bottom of this plaster, and then the half symmetry on the right, and then the water in this plaster evaporates. So we let water evaporate from these surfaces. And this is the simulation result of the pressure of the fluid pressure first. So as you see that near the boundaries, it developed negative pressure. So that's when it loses the water saturation. And also, as you see, we use a very coarse mesh. So only 3,700 elements in here, and then all structured element, and also material properties was homogeneous. So meaning that we in this model, in this domain, there's nothing to trigger any structure, right? So the mesh is uniform, structured, and material properties are all homogeneous. So there's nothing that can trigger fracture development. So this is how the fracture developed. So first, we saw some fracture development on this lower bottom corner, and then some vertical cracks started developing, and then we saw more vertical cracks, and then at some point it reached some saturation point of the cracks, and then we did not see any new crack development. Yeah, but all these nucleation of the fractures were picked up based on the energy minimization. Okay, and another example. Well, this is again desiccation cracking, but we applied to this tunnel system. And so this is the cyclic deformation experiment I showed you in the beginning. So the humidity in this chamber was controlled and then cyclically changed. And as a result, so this is just a simulation result, but we simulated that the crack will develop like this. Okay, I should have put some pictures, but this looks very much like what you see on the ground after a rainy day. This pattern of the crack looks very similar to such a desiccation crack. Okay. All right. So I just have one more example that I would like to show, and this is about hydrofracturing. Okay. So here in 2D, I simulated the hydraulic fracture interaction with a natural fracture. So I placed some initial fracture, and then I placed natural fracture some distance away from this initial fracture with some angle. So I simulated two cases. One is 90-degree case, and then other one is the 165-degree case. So this black line represent natural fracture. So natural fracture is represented with reduced fracture toughness. So this is some weak material in this black part. Okay. So so each angle I use two different strengths of this natural fracture. So the actual values are not very important, but let's say one is strong and then other one is weak. So this is the strong natural fracture case, and then this is the weak natural fracture case. And the strong natural fracture case, the hydraulic fracture just ignore the existence of this natural fracture, and then it bypassed it and propagated straight. And when we reduce the strength of this natural fracture, it branched on this natural fracture. So it's split into two ways, and then it followed this natural fracture. And when we change the angle, so the fracture approaching angle is smaller in this case. Two different strengths of the natural fractures, and strong and weak in both cases, the hydraulic fracture propagated along this natural fracture. Okay, so that's all I have for examples. Then I just give you some of my conclusions. So a variational phase field model is an appealing predictive tool for initiation and also complex fracture propagation simulation. And so this approach is gaining popularity, and it's extended beyond elastic brittle materials. But it just started coming to this subsurface field or hydraulic fracturing field. So we still have a lot of things to do for geomaterials. Okay, so with that, I conclude my presentation, and I like to acknowledge my collaborators. And I'm happy to take any questions you might have. Thank you very much.
Hey, thank you so much, Keita. That was really informative, and you've generated a few questions. And so maybe if you can either read them or I can read them out.
Okay. Yeah.
So the first question is from Ed, and Ed wonders, in your formulation, shouldn't the phase frac parameter be directly coupled to the fracture width W somehow?
Yeah. So the fracture aperture, right? So yeah. So the fracture width, we recover fracture width from we will recover fracture width from the deformation. So coupled directly with the phase variable. No, it's not coupled. So the phase variable tells us whether the material is broken or not broken. But the fracture aperture. So even the fracture, even the material is fully broken, meaning that the B is completely zero. But there could be a case where fracture is completely closed, and then fracture aperture can be zero. And we have So the fracture aperture is coming from the deformation, but the existence of the fracture is coming from the phase field variable. So the phase field variable gives us an indicator, and the actual value of the fracture aperture has to come from the deformation or the displacement.
Okay, great. And so Uno has a question, and his question was, do you use adaptive mesh refinement within the framework of the phase field model? And he also says it was a big presentation.
Yeah, so about the adaptation, no. In our model, we don't have the mesh adaptation. If he means by dynamic adaptation, no, we don't have it. We like to have it, but we just don't have it. And the second question about perturbation. So no, so that's actually the point I like to make. So we do not need to give it any perturbation. Fracture nucleation is a result from the energy minimization. So okay, maybe if I go to the very first slide on this example. Okay, I don't know. Yeah. So this is also a nucleation of the fracture, and as you see, the damage is initially developed uniformly. So everywhere there's a damage, uniform damage. But in this evolution process, at some point, this uniform damage becomes unstable. meaning that so if we compare a two state of energy, one has a localized damage and the other has the homogeneous uniform damage. And if we compare the energies of these two different states, and then localized damage has a lower state of energy, that is more stable than the uniform damage state. So that's when the damage starts to localize. So initially damage is uniform, as you can see, but then at some point it starts to localize because uniform damage is no longer stable. Okay. Hopefully that answers the question.
I think it did.
Yeah.
So there's another question from Ed, and he's wondering, in the you showed the desiccation problem, the rectangular configuration, and you started with a uniform mesh and uniform property. And he's trying to understand what drives the nucleation, and would you see a different nucleation pattern if you ran the simulator in single versus double precision? So what drives the nucleation?
Yeah, so what drives the nucleation is I think is same as before. And then the second question, so the if we see a same pattern, so that goes to uniqueness, uniqueness of the crack, and so that's the well that depends. So if we have so again, so this is the energy minimization problem, right? So our implementation does not guarantee to find a global minima. We can only find local minima of the energy. So the uniqueness is not always guaranteed. Okay. So so let's say the number of cracks will not change. So if we have two vertical cracks, then two cracks will be the solution. But the exact location of these two cracks, let's say, could be a little bit different. And if the energies of these two states, so two slightly different locations of two vertical cracks, if the energies of these two states are almost the same, we cannot guarantee to find the global minima always. We can only find the local minima. So so for nucleation process, that can happen. But if we have a very clear stress concentration, so let's say like hydraulic fracture propagation, and we have a stress concentration at the crack tip, and then the minimization problem is simple. In that case, almost always local minima and global minima coincide, so we don't have such issue of uniqueness.
Thank you. And Yue's question is he's wondering if the model has the capabilities ultimately of dealing with an anisotropic material.
Yeah. Yeah, thank you for the question. So I didn't show any example, and yeah, we just recently added anisotropy. We have not tried it with hydraulic fracture yet. Just a pure mechanical process. We implemented orthotropic anisotropy. It's because the nuclear waste disposal case. If people are familiar with this opalinous clay, and it's a very anisotropic material, so we wanted to simulate this clay material. So we added anisotropy. We have yet to couple it with the hydraulic fracture.
Excellent. So the next question was from Josiah, and Tao actually gave an answer to it, but I'm going to give you a chance too. So what software is used to develop the model?
Yes. Thank you for the question, and I should have mentioned. So So this is open source code called OpenGeosys. So I am a part of development team. Yeah, I should have put some link or something, but I did that in acknowledgement. So the OpenGeosys, this is this is the name of software, and this is maintained at the Helmholtz Center in Germany.
Excellent. And
Yep.
then the next question, first of all, thanking you for the presentation, was does the phase field interface correspond to the actual fracture width? And considering the variation of the fracture width from its source.
Yeah. So no. So the phase field can be considered as a special model of the damage mechanics, or non-local damage mechanics, and as is the case in damage mechanics, so the fracture is diffuse over multiple elements, and the actual fracture is somewhere in this multiple elements. So you know, that's the difficulty of the fracture, right? So the fracture aperture is in the orders of millimeters, and then using the damage mechanics or the phase field model, we represent this millimeters aperture of the fracture using several elements, multiple elements, which goes to orders of half meter or so. So the actual fracture is somewhere in there, but we should not take this diffuse fracture as actual fracture. The actual fracture is somewhere in this diffuse fracture, and then you know, there are some people who research how to recover the actual fracture path, identify the real fracture path from this diffused image. Yeah, so it's just a mathematical representation or numerical representation of the soft fracture.
Cool. So Uno, there's another question, and about nucleation. And do you introduce a perturbation in some of the models to trigger fracture initiation, e.g., some sort of physical heterogeneity?
Yeah. So the example that I showed today about the discussion crack, no, I did not introduce any this perturbation, and also that's the reason I used the uniform and structured element, because I didn't want to introduce any sort of bias in the mesh or the material property.
So then Zenaidia had a question, and are there some analytical approaches for crack initiation propagation if you're considering poroelastic materials?
Yeah, analytical approaches. Yeah. So well. Oh, okay. So let me start with elastic material. So the elastic material in simple loading, yes. So like 1D, like uniaxial tension or uniaxial compression, yes. There's a closed form solution for phase field, and the poroelastic model. So so discussion crack. I think it's possible if we assume some kind of evaporation rate. But hydraulic fracturing, yeah, I'm not sure. Well, yeah, it's probably very difficult. Yeah.
Okay.
Yeah.
Fair answer. Now, here's the toughest question. Here's the toughest question to date: is how is getting the code into 3D going?
Peter
would like to know.
Well, the code is 3D. The code is 3D, but I just need a bigger computer. I showed some 3D examples, but you know, I'm in academia now, so I don't need to run 3D models. Well, not all the time.
Um, so Mojtaba would like to know, how are the parameters of the phase field model determined and fixed, and how do we assume that those are selected realistically?
Okay. Yeah, thank you for the question. And this is actually active area of the research. So so we don't need many parameters. So so it's, well, if we just simulate the linear elastic fracture, so we only need a Young's modulus Poisson's ratio and then the fracture toughness G of C. That's a property required for linear elastic fracture mechanics. And then we only need one additional parameter, which is length scale, L. And so there's active research how this length scale impacts the physical property. So initially, this length scale was introduced as a regularization parameter. So it's just a pure mathematical parameter, but some people relate this L with the physical properties such as process zone and so on. So if our interest is fracture nucleation, then this length scale plays a big role. And then there's a way we can relate this length scale with a physical property. So if we measure the uniaxial tensile strength or uniaxial compressive stress, then we can derive this length scale parameter. But sometimes this length scale parameter gives us non-feasible values such as 1 millimeter or so. Then we will need an element size of the 1 millimeter or less. Then that's not really feasible. But that's the case for fracture nucleation. And for fracture propagation, this length scale, the effect of this length scale, we can remove it. Actually, I cannot explain by detail, but for propagation problem, we can remove the effect of this length scale parameters. So yeah, so it depends on the problems that you want to solve. Yeah.
So great. I think that was Mojtaba's next point. Yeah. And so Josiah wants to know, we've seen you can do desiccation. Can you do chemomechanical processes?
Yeah, that would be great. And actually that is one thing we are working on right now. We don't really have any results yet. But yeah, that's certainly a direction we're heading at the moment. Yeah.
And then
but not
Lee,
yet. Yeah.
Not yet, but one day.
Yeah. Yeah.
So Lee, let's see. In the bending test on the cover page, you're showing grain scales.
Yeah.
How did the grain scale parameters identified? And do you have any comments on determining micro parameters for the small scale simulations?
Yeah. Thank you for the question. So how did we determine the how to identify the parameter? Okay, so this was so here these grains are just generated statistically, and so there's some code that generates a polycrystal material, and we only need to provide statistical parameters like average grain size and so on, and then we get this polycrystal material, and then so this was just this is something that we are studying at the moment, but and then the grain parameters. Okay. Okay. Yeah. So it's not easy to get the grain parameters or properties of minerals. But in this particular simulation, we we found some literature who came up with this grain properties used in a molecular dynamics simulation. And for example, like a Young's modulus for fracture toughness for silica and so on. So that's so we didn't derive the properties, but there was some study that generated properties using a molecular dynamics simulation. So that's how we got the data.
Yeah, it's always a challenging issue. And then the final question was, will the recording be available? Yes, the recording, this, I did remember to record this, and it will be uploaded to the ARMA's website, probably within a week. And if anybody wants a specific link, just send me and just send me an email. And I also suggest that if you have any specific questions that you'd like to ask Professor Yoshioka, that you, Keita, you'd be interested in people communicating directly with you, I'm sure.
Yeah, no problem.
So this generated a lot of questions. This was fantastic. I mean, really a tremendous amount of interest. Very versatile method, and a tremendous presentation. So thank you so much.
Thank you very much for the invitation. I enjoyed it a lot.
And thanks for everyone for attending.